In this video, we're going to review Unit 8 so that you can prepare for taking the quiz and the performance task. So, what we're going to start with first is drawing some Lewis structures for these molecules. So I'm going to go over some of the steps that you should use so that you can check your work and make sure your structures are correct before you move forward. Because if your structures are incorrectly drawn, then everything after that will be also incorrect. So what we're going to do first is do our electron count. So what I'm going to do is I'm going to start by writing down the atoms that I have in the structure, which is C, carbon, H, hydrogen. And then what I'm going to do is I'm going to look up the group number, which is going to let me know the number of valence electrons that that atom has. That's the short way of figuring it out without having to draw a model for it. So since carbon is here in group 4, see, okay, there it is. So since carbon is in group 4, it's going to have 4 valence electrons. And then hydrogen is over here and it's in group 1, so it's going to have 1 valence electron. And then what I'm going to do is I'm going to multiply by the subscript. The subscript are the numbers here in the chemical formula. So remember, if you don't see a number, that doesn't mean it's 0. It's always 1. So it's never 0. It's always 1. So this formula is saying that I have 1 carbon and 4 hydrogens. And then I'm going to multiply those numbers together. So 4 times 1 is 4. 1 times 4 is 4. And I'm going to add those together. 4 plus 4 is 8. So that means I have 8 total electrons. So this is just my electron count. So this is going to help me double check my work at the end. Next thing I'm going to do is I'm going to draw the Lewis dot structures for carbon and hydrogen so I can figure out how many bonds each one can make. So carbon, again, since it's in group 4, which is shown here, it's going to have 4 single electrons. And then hydrogen, which is in group 1, is only going to have 1 single electron. The single electrons, meaning the electrons that do not have a pair, they can make bonds. So that means carbon can make 4 bonds and hydrogen can make 1 bond. Next step after this is now I'm going to put all of this together to make my structure. So whichever atom makes the most number of bonds, that's the one that's going to go in the center of my structure. So since carbon has 4 bonds it can make, and hydrogen can only make 1, that means in the center of my structure, I'm going to have carbon. So carbon, I'm just going to copy the Lewis structure exactly the same. And then I'm going to add in my hydrogens so that they can bond with carbon. And then once I finish drawing my structure, now I'm going to check my work. So if this structure is correct, 2 things are going to be true. I'm going to have a total of 8 electrons. Each carbon is only going to make 4 bonds, and each hydrogen is only going to make 1 bond. So if I look at this, and remember that each bond counts as 2 electrons. So when I count this, it's going to be 2, 4, 6, 8. So I have 8 valence electrons. And then if I look at my structure, carbon is making 1, 2, 3, 4 bonds. So carbon's happy. And then hydrogen is making each just 1 bond. So this is 1, this is 1 bond, this is 1 bond, this is 1 bond. So this checks out. I have a total of 8 electrons. Each carbon is making 4 bonds. Each hydrogen is making 1 bond. So everything's looking good. So that's my structure. Next step, step number 2. Identify and count the polar bonds. Show all electronegativity differences and color code all bonds. So we're going to use the electronegativity chart for this. And we're going to start by writing down the electronegativity values for each atom. So carbon, according to this chart, has an electronegativity value of 2.5, which is shown right here. So I'm going to write 2.5. And then hydrogen, which is over here, has an electronegativity value of 2.1. And then what I'm going to do is I'm going to subtract those numbers. And we always do bigger number minus smaller number, so you should never have any negative numbers for this. And this is equal to 0.4. So according to this, if it's between 0 and 0.4, I'm going to highlight these yellow because those are nonpolar bonds. And if the difference is between 0.5 and 2, I would highlight it blue. That would mean a polar bond. So since the difference between them is 0.4, I'm going to highlight that yellow. Another thing is, since these are all the same bonds, I have CH, 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 I don't have to subtract this 4 times because it's going to be the same regardless. So I just have to do this once, and then I'm going to highlight all of these yellow. All right, so that's done for step 1 and 2. Now we're going to move on to step number 3, which is figuring out if this entire structure is symmetrical or asymmetrical. So what we're going to do is we're going to pull up this chart, the VSEPR chart, and we're going to use the shape of it to try to figure out if it's symmetrical or asymmetrical. So the way you use this chart is you have to always look at the central atom, and you have to count how many groups are around the central atom. We have 1, 2, 3, 4 groups around the central atom. So that means I'm going to look on this chart at row 4, and then the way you read the columns up and down is based on the number of lone pairs. So how many lone pairs are on the central atom? So if we look at carbon, there are 0 lone pairs, only bonds. We only have bonds, no lone pairs. If you forget what that looks like, this is a lone pair versus this is a bond. So our carbon has no lone pairs around it. So that means when I'm looking at this chart, I'm going to stay on row 4, which is this, and I'm going to focus on this column right here, which means this would be the shape of this structure, tetrahedral. What I want to use is this color-coded chart to tell me if this is symmetrical or asymmetrical. So based off this chart, this structure will be symmetrical, which means there is equal sharing of electrons. Next step is we have to figure out if this molecule is polar or non-polar. So overall, is this a polar molecule or a non-polar molecule? PB stands for polar bonds, and then A stands for asymmetrical. So I'm going to pull up this chart that you have in Noteful. It's just zoomed in, so which is determining the IMF chart. So we are right now on step number 4. Determine if it is a polar molecule. We already did steps 1, 2, and 3. So we drew the Lewis structure, we identified and counted the polar and nonpolar bonds, we determined if the molecule is asymmetrical or symmetrical. Now we're on this step. So in order for this molecule here to be considered a polar molecule, 2 things have to be true. You must have polar bonds, and you must have this molecule be asymmetrical, meaning unequal sharing of electrons. If you cannot check off both of these boxes, that means you do not have a polar molecule. So let's look at ours. Do we have polar bonds? No, so I'm not going to check that box off. Is this molecule asymmetrical? Also no, so I'm not going to check off that box. That means that this molecule is not a polar molecule, so I'm going to circle no. And now the last step, which is choosing the strongest IMF. So we have 3 options, either LDF, dipole-dipole, or hydrogen bonds. But really we only have one option. Since we figured out that this is a non-polar molecule, that means that the strongest IMF that this could have is actually just LDF. So if it's a non-polar molecule, automatically the strongest IMF is LDF. We can't have dipole-dipole or hydrogen bonds. These are only for polar molecules. So our strongest IMF is LDF. All right, now we're going to go and look at the next structure. So again, we're going to go through this. We're going to first start by drawing our Lewis dot structure with Lewis dot structures, which means we have to do our electron count. And I would recommend you do this for the quiz so you can check your own work before you complete it, just to make sure that everything's looking good and you're not just losing points endlessly. All right, so now what I'm going to do is, again, I'm going to use the group number. So carbon is in group 4, so I'm going to write 4. Chlorine is here in group 7, so I'm going to write 7. And then fluorine is also in group 7, so I'm going to write 7. And then we're going to be multiplying by the subscript. which is given to us in the chemical formula. And again, if you do not see a number, it is never 0, it's always 1. So that means I have 1 carbon, I have 2 chlorines, and I have 2 fluorines. And then I'm going to multiply these. So 4 times 1 is 4, 7 times 2 is 14, 7 times 2 is 14. Add all of these numbers together. So we have 8, 9, 10, 11, 12, 32 total electrons. So that's my first thing I'm going to do is my electron count. Second is now I'm going to draw my Lewis dot structure. So carbon, since it's in group 4, it's going to have 1, 2, 3, 4 valence electrons. Chlorine, since it's in group 7, is going to have 1, 2, 3, 4, 5, 6, 7 valence electrons. And then fluorine, since it's also in group 7, is going to have 1, 2, 3, 4, 5, 6, 7 valence electrons. All right, next I'm going to try to figure out how many bonds can each of these atoms make. So remember, the single electrons are the ones that tell you how many bonds they can make. So carbon can make 4, chlorine can make 1, and then fluorine can also make 1. Now that I figure that out, what I'm going to do is I'm going to start to put this together. So whichever atom makes the most number of bonds is going to go in the middle, and then the other atoms that make less bonds are going to go on the outside. So this atom is going to go in the center, and then the other atoms, I'm going to start to place them on the outside. And then I'm also going to make sure I draw in their lone pairs of electrons. And now what I'm going to do is I'm going to do my count to make sure that I have 32 total electrons, and I'm going to double check the number of bonds each atom is making. So if I look at this, I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So that checks out. I have 32 electrons. And now let me look at my bonds. Carbon is making 1, 2, 3, 4 bonds, so carbon is happy. My chlorines are each only making 1 bond, so they're happy. And then my fluorine is only making 1 bond too, so that one is also happy. So all of my atoms are happy here. This is a correct structure. I can move forward now. So the next step is counting and highlighting my polar and nonpolar bonds. So this again is when I'm going to need my electronegativity chart. So I'm going to write down the values or the electronegativity values for each atom. So carbon is 2.5, so I'm going to write that down. So carbon is 2.5, chlorine is 3, and then fluorine is 4. And then I have to take the difference for each bond that I have. So I have a carbon-chlorine bond. I actually have 2 of them. Here's one and here's another one. So I'm going to subtract those. So we have 3 minus 2.5 is 0.5. So always bigger number minus smaller number. And then I have a CF bond. So I'm going to subtract those too. So we have 4 minus 2.5. That should be 1.5. And now what I'm going to do is I'm going to look at those values and compare that to this to figure out if I'm going to highlight this blue or yellow. So I have a difference of 0.5, which means that would be polar. And I have a difference of 1.5, which also means it would be polar. So that means all my bonds, I'm going to highlight them blue to show that they're all polar bonds. Now I can move on to the next thing, which is this molecule symmetrical or asymmetrical? So I'm going to have to pull out my chart, which is this one. And looking at carbon, I have 1, 2, 3, 4 groups around carbon. So once again, I'm going to look at row 4. And then if I have any lone pairs, which I don't because I only have bonds around carbon, that means I'm going to still stay within this same group or the same column. So that means if I look at this, it matches up with this shape tetrahedral because I have 4 bonds around my central atom and 0 lone pairs. And using this chart, initially, this says that this is symmetrical, that all 4 bonds are sharing equally. However, if you look at the structure that we have here, That is not true because not all 4 bonds are the same. We have CF, CF, CCl, CCl. So since not all 4 bonds surrounding the carbon are the same, this is actually not equal sharing of electrons. So I'm going to say that this is asymmetrical. Even though on my chart it says it is symmetrical, that's only true if all the bonds are the same, which they're not. I'm going to move on to the next thing, which is figuring out if this molecule is a polar molecule. So on my structure, I do have polar bonds, and I can tell because they're highlighted blue. This structure is also asymmetrical, which means yes, I do have a polar molecule. Now the last step is figuring out what's the strongest IMF. Well, I have 2 options for my strongest IMF since I have a polar molecule. This structure can either be dipole-dipole, or it can be a hydrogen bonding as the strongest IMF. Dipole-dipole means we have a structure that has polar bonds that are not hydrogen bonds. And a hydrogen bond as your strongest IMF means you have a polar molecule that has either HF, HO, or HN. And it has to look exactly like that. Just because you have a hydrogen does not mean you have H bonding. So if we look at our structure, it does not look like we have any HFs, HOs, or HNs, which means our strongest IMF has to be dipole-dipole. All right, let's look at this last structure. So again, we're going to go through all of these steps. First step being drawing the Lewis dot structure. So what I'm going to do is I'm going to write out the atoms that I have, and I'm going to use the group number from the periodic table, and I'm going to multiply that by the subscript, which is given to me in the chemical formula. So nitrogen is in group 5. So nitrogen is in group 5. Hydrogen is in group 1. And I'm going to multiply by the subscript. So again, that's from the chemical formula. If you do not see a 1, don't assume it's 0. It's never 0. It's always 1. So I have 1 nitrogen and then I have 3 hydrogens. 5 times 1 is 5. 1 times 3 is 3. I'm going to add these together, and that gives me 8 total electrons. Next thing I'm going to do is I'm going to use the group number to draw my Lewis dot structures. So since nitrogen is in group 5, it's going to have 5 valence electrons. Since hydrogen is in group 1, it's only going to have 1 valence electrons. And then the single electrons are the ones that tell you how many bonds you can make. So nitrogen has 1, 2, 3 single electrons, so it can make 3 bonds. Hydrogen has only 1 single electron, so it can only make 1 bond. Whichever atom has the most number of bonds is going to go in the center. So if we're looking at this, nitrogen has 3 bonds that it can make. Hydrogen only has 1. So that means nitrogen is going to go in the center of my structure. And I'm going to add in my hydrogens. Remember that this lone pair means it cannot make a bond. So that's why we're not adding the hydrogen there. So anytime you see a lone pair, that's not making a bond. Those are just on that atom. Now what I'm going to do is I'm going to double check my work. So if this is correct, we should have only 8 total of electrons, and then each atom can only make this number of bonds. So if we count, we have 2, 4, 6, 8. So that's good. That checks out. If we look at the bonds, nitrogen is only making 1, 2, 3 bonds, which is good, and each hydrogen is only making 1 bond. So both are correct. So this is my structure. Now I can go ahead and use my electronegativity chart to figure out what type of bonds do I have. Do I have polar bonds or non-polar bonds? So nitrogen has an electronegativity of 3. Hydrogen has an electronegativity of 2.1. Remember, bigger number minus smaller number. So this is going to be equal to 0.9. And if I look at my scale, since it's between 0.5 and 2, that's going to be blue. So I have some blue polar bonds. So I'm going to highlight these blue. And now I can move on to the next step, which is figuring out if this structure is symmetrical or asymmetrical. Alright, so now I'm going to look at my group. are the groups that I have. So nitrogen is right here, and it has 1, 2, 3, 4 groups surrounding it. So I'm going to look at 4. And then this one has 1, 2, 3 bonds, but it does have 1 lone pair. So I'm going to look at row 4, but now I have to look here at this column because this is the column that has 1 lone pair, which means my shape is trigonal pyramid. That also means that this structure is asymmetrical, meaning it is not sharing those electrons equally. Another way you could tell is usually whenever you have lone pairs on your central atom, that is making those electrons, all the electrons in the structure, spends more time with that lone pair of electrons, and it starts distorting the shape. So usually when you have lone pairs on your central atom, that leads to unequal sharing of electrons, which means your structure would be asymmetrical. Next thing we're going to do is we're going to check to see if we have a polar molecule. So it looks like we do have polar bonds because they're highlighted blue, and this structure is asymmetrical. So since both of those two things are true, we do have a polar molecule. Last step is figuring out, okay, what's the strongest IMF? So since this is a polar molecule, we have two options. It's either going to be dipole, or H bonding. So what we're going to do is we're going to look to see if we have an H bond, which is HF, HO, or H bonded to N. So it needs to be F, O, or N. If we look at this structure, it looks like we have multiple H bonds. So we have HN, HN, HN. So that's 3. So this strongest IMF is H bond. All right. So now that we have done all of this work to figure this out, we can use what we know about the IMFs to be able to place this from lowest to highest boiling point. The strength of the IMF is telling you how strong of a boiling point, or how low or high of a boiling point that's going to be. So I'm going to put the low on this end and then high on this end. So the lower or weaker IMFs is going to have a lower boiling point, and then the stronger IMFs are going to have a higher boiling point. So that means since LDF, and I'm basing it off this chart, which is showing you the direction of which this is increasing. LDF is the weakest, dipole is in the middle, hydrogen bonding is the strongest. So based off this, that means I should predict that CH4 is going to have the lowest boiling point. CCl2F2 is going to be in the middle, and then my NH3 is going to be the highest because it has an H bond. The other thing I'm going to do is now I'm going to explain it. So this is going to be in using the vocabulary, explaining like what's happening with this. So CH4 has the weakest IMF, which stands for intermolecular force. And I'm going to put in parentheses which IMF it has, LDF, making it have a lower boiling point. And then the next compound, CCl2F2, has a dipole, IMF, which is stronger than LDF, but not as strong as an H bond. NH3 has the highest boiling point, due to having the strongest IMF. Which is the H bond. Alright, so that's an example of what you can write to explain your ranking. You are not limited to this, but this is just to give you some ideas. Alright, we're going to move on to the next couple questions. So these questions are coming from some of your Noteful sections. We're going to go through these together and talk about them. So the first one is, as you move down a group on the periodic table, the boiling point increases or decreases. So the trend is, as you move down a group on the periodic table, the boiling point is going to increase. Therefore, boiling point and molecular size are directly related. So as an atom gets bigger, the boiling point increases. Longer stretched out molecules have higher or lower boiling points than compact molecules. The more stretched out or branched out the molecules are, the higher the boiling point is. The more condensed they are, the more closer those atoms are together, the lower the boiling point will be. The next one, carbon number and boiling point are directly or inversely related. This is directly. So the more carbons you have, the higher the boiling point, and vice versa. The less carbons you have, the lower the boiling point. Next, we're going to use those vocab words to fill in these blanks. So intermolecular forces are caused by differences in charge, which is originally caused by electronegativity differences between atoms. At room temperature, gases like Ne, Kr, O2, N2, etc. have higher or lower boiling points than blank, which have higher or lower boiling points than solids. So gases are going to have lower boiling points than liquids, which have lower melting points than solids. Polar molecules must have blank and blank. Well, we were just looking at that. Polar molecules must have polar bonds, and they need to have asymmetry, meaning there's unequal sharing of electrons. So they need to be asymmetrical. List 3 intermolecular forces in order from least to greatest. So I'm going to list the 3. We have LDF, or London dispersion, force, that's LDF, which is the least or weakest IMF. Then we have dipole-dipole, and then the strongest is hydrogen bonding. Alright, next one. We're going to compare these two compounds by highlighting and identifying polar and nonpolar bonds, and then doing a little bit of counting on this. So I'm going to use that electronegativity chart to identify what atoms I have, and then what's the difference between them. And if you look at this structure that we're looking at first for caffeine, it looks like we have a lot of the same bonds repeating. So we have CH, CH, CH. That happens quite a couple times, so I'm going to start by writing that down so I can figure out what the difference between them is. I also notice I have a couple times where C and N are bonded to each other. And then let's see, what else do I have? CC, there's a bond when CC is bonded together. What else? CO, that's another bond I can identify. And I think for right now, that's it. Those are the different types of bonds that I have. Alright, so now what I'm going to use is that electronegativity chart to figure out what's the difference between these, so that I can start figuring out how many polar bonds and nonpolar bonds I have. And we're always going to do bigger number minus smaller number. So carbon has an electronegativity of 2.5. I'm subtracting that from hydrogen, which has a value of 2.1. So this is going to be equal to 0.4. And then once again, I have carbon, but this time it's bonded with nitrogen. Nitrogen has an electronegativity value of 3. And I'm going to subtract that from carbon, which is 2.5. It's going to be equal to 0.5. And then carbon and carbon bonded together, so that's going to be 2.5 minus 2.5, and that's going to be equal to 0. And then carbon and oxygen. Oxygen has a value of 3.5, subtracting that from 2.5, and then I should get 1 as my answer. All right, now that I figured all that out, I can do some highlighting. So remember, if it's between 0 and 0.4, according to this, that would be nonpolar, and if it's between 0.5 and 2, that would be polar. So I'm just going to write this here again so I can remind myself. If it's between 0 and 0.4, nonpolar. If it's between 0.5 and 2, polar. So let's see. I have my CH bonds are 0.4, so that means I'm going to highlight all my CH bonds yellow for nonpolar. So that's nonpolar right there, nonpolar, 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 nonpolar. And I think those are all of them. Now let me go to the next bond, which I have CN. The difference between them was 0.5, which means this is going to be a polar bond. So I'm going to highlight all my CNs, a polar bond, blue. So that's CN, 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 and it doesn't matter if it's a single or a double bond. Anytime I see CN, I'm going to highlight those blue. Okay, next one. CC, the difference between them is 0, which means they're equally sharing electrons. I'm going to highlight those yellow because those are nonpolar. Okay, and then the last type of bond I have is CO, and the difference between that was 1, and that's going to be blue for polar, so I'm going to highlight those bonds blue. So blue and blue here. All right, next thing I'm going to do is now I'm going to do a little bit of counting. So this is asking me to figure out, okay, how many hydrogen bonds do I have? So remember, that doesn't mean that we have hydrogens in the bond. It means we either have an HF, an HO, or an HN. And if we look at this structure, I'm looking here, and I don't see HF, HO, or HN. So I'm going to put a 0 for that. So remember, if we don't have hydrogen bonds, that means that our polar bonds have to be dipole-dipole. So let me bring up this chart again to show you. These are for our polar bonds. But if we don't have H bonds, that means automatically all our polar bonds are going to be dipole-dipole. So that means we have on this structure 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 dipole-dipole bonds. And then all our yellow nonpolar bonds are LDF bonds. So I'm going to count those. And I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Ions means, do I have any like positive or negative charges on my structure? And if I look at this, it does not look like I have any positive or negative structure, so I'm going to write 0, or you can say none. And then the carbon numbers. The carbon number, you could count them, or you could just look at the formula and write that number down. So it's C8, so I have 8 carbons. All right, so that's the first structure. Now let me look at the next structure. This one looks a lot easier to figure out the difference for, because if I'm looking at this, really I only have 2 types of bonds. CC, carbons bonded to each other, and CH. So now what I'm going to do is I'm going to use my electronegativity chart. Write down those values. So it looks like carbon is 2.5. So 2.5 minus 2.5, it's going to be 0. And then carbon, again, is 2.5. I'm going to subtract that from hydrogen, which is 2.1. That gives me a difference of 0.4. So now I can highlight my polar and nonpolar bonds. So it looks like for my carbon, since that's 0, that's going to be nonpolar. And since the CH is a difference of 0.4, that's also going to be nonpolar. So I'm actually going to be highlighting all of these yellow, to show that they are all non-polar molecules. So highlighting all of those yellow. Alright, so now we're going to do a count. So remember, hydrogen and dipole-dipole, these are polar bonds. So we don't have any polar bonds because nothing is highlighted blue. So right off the bat, I'm going to put a 0 for both because we have no blue polar bonds. What I do have is a bunch of LDF bonds, so I'm going to count them to see how many I have. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So I have 19 LDFs. Ions, remember, that means, do I have any positive or negative charges? Nope, I see no positive charges. I don't see any negative charges, so I'm going to put 0 or none. And then carbon. So again, I could count the carbons, or you could just look at the formula, and I have 10 of them. Alright, so the purpose of looking at these two compounds were to compare them, and then essentially just practice writing like a little ERC. My evidence, so I have caffeine has a melting point of 235 degrees Celsius. Naphthalene has a melting point of 177 degrees Celsius. Explain why. So that's what we're going to do next. We're going to explain why caffeine has a higher melting point, and what we're using as our evidence and our reasoning is coming from these charts. It's based off these numbers here. So I'm going to start to write down what's happening here. So we have caffeine has a higher melting point than naphthalene because it has dipole. It has 13 dipole bonds as the strongest IMF. Which is stronger than naphthalene's 19 LDF bonds. So the dipole bonds here overpower the LDFs, which means that's why caffeine has a higher melting point. Alright, so that's it for this review. Hopefully that helps you out, and good luck when you're taking the Unit 8 review, or the Unit 8 quiz and Unit 8 performance task.